Yeah, okay, great. So that's allow me to pitch it. I'm probably pitch it, towards, this is supposed to be an introduction towards the lower end. So we'll certainly start off pretty basic and then hopefully pick up some perhaps more complicated things towards the end. I'm going to cover a lot of the stuff that Neil covered before in maybe a different way with some slightly different pictures. So I'm going to start off by motivating this with nonlinear regression, sort of the similar way that Neil did. So let's imagine, fortunately we've used the same notation for most of these slides. I did do a Control F and replace lots of things when I saw some of Neil's slides. So some things may have slipped through which have slightly different notation, but I think in general we're pretty well in synchrony here. So imagine we're doing a nonlinear regression problem. Here are our input points x, and we've observed some observations y here at a bunch of input points. And what we're really interested in is questions like, what's going on at this input point here where we haven't seen an observation particularly close to it? Could I predict what the function's doing along this line? Where's it cutting this line? And what is the uncertainty around that function at that point? And I'll be motivating Gaussian processes as a way of solving this sort of problem, but in general you should think of them as useful things for just putting priors on nonlinear functions, so encapsulating our prior beliefs about the sorts of functions we'd hope to see in a particular situation. Nonlinear regression is just a particularly simple example of that, and so easy to describe. Okay, so the idea is we're going to do this with just a plain old Gaussian, as you've seen in Neil's talk, and it's perhaps slightly surprising we can do this with a plain old Gaussian. So here's a very brief recap of the Gaussian distribution. Neil's covered this before, so this should be sort of very familiar territory. The probability of a vector of observations given a covariance matrix is proportional to an exponentiated quadratic, to use Neil's term. This is the data, yt. There's a covariance matrix which is sitting inside here, and in this two-dimensional case we can express the covariance matrix as this 2x2 matrix here, where these entries here are the variance in the y1 and y2 directions, and this is the correlation between y1 and y2. And we can also draw samples from the Gaussian distribution. I think we should all be sort of fairly comfortable with that. And there are packages for doing this on MATLAB and in Python. And as I change the correlation of the Gaussian, so these off-diagonal elements of the covariance matrix here, I can turn it from something that was very correlated, where y2 was dependent on y1, to something where there's no dependence between these two different dimensions of the data set, and here we get an isotropic Gaussian. Okay, so let's go back to our correlated Gaussian, because that's going to be the workhorse underneath Gaussian processes. And let's consider very quickly the second operation we might want to do here, which is conditioning. So imagine somebody comes in and tells us, I know the value of y1 to be precisely equal to 1. What do we think y2 is taking on? What value is y2 taking on? Well, Neil talked you through this, and we'll go through this in a bit later, but that distribution also magically is Gaussian. It was obtained by, as Neil said, taking a slice through this Gaussian at this point and then renormalizing the density we get along that line. And that's a Gaussian with a mean equal to mu star, and the mean's just in here. Got a little picture of that. Here's the mean, and a variance, or more generally, if y2 was a vector of variables, a new covariance matrix here, which tells you the width of that distribution. And there's some nice properties of these quantities. For instance, it turns out that mu star, the estimate for this mean, is just linear in the things we have observed, where these w's depend on the form of the covariance matrix. Okay, so a nice simple relationship between the mean of this Gaussian and the things we've observed. All right, and we could also draw samples from this conditional distribution as well, so straightforwardly, in exactly the same way. And again, if we change the correlation between these variables, we change the shape of that conditioning distribution. So if they're independent from one another, observing y1 tells us nothing about y2, and we get relatively broadly separated samples. Okay, so this should be Gaussian 101. Hopefully everyone's happy with this. And now what we're going to switch to is a new way of visualizing what's going on. And so I plotted the same thing we saw before up here with a sample. This is a correlated Gaussian with a sample from it here. And here's our covariance matrix, just as before, sitting down here. And what I'm now going to do is plot this in this different way, where y is in this y coordinate here. And the distance of this sample here So this distance along here, along the y1 axis, is going to be plotted as a horizontal height above the variable index here. This is variable index 1. Okay, so we plonk this one, this guy, y1, is about at the value 2, and so this thing is sitting roughly at the value 2. And I can do the same thing for the other dimension of this two-dimensional Gaussian. So what's the height of this sample? Well, I'll plot that as a vertical height in here, in exactly the same way. Okay, so everyone's super clear with this. This is just a new way of plotting exactly the same thing I showed you before. And I can now take samples of this correlated Gaussian distribution and plot them in the two different ways that we've seen them before. And because observed dimension y1 is fixed to 1, and now we can sample over the second dimension. And so this thing just wiggles around here as we sample from the conditional. Things are wiggling around much more because this was a correlated Gaussian, and so conditioning on y1 severely restricted sort of compatible values with y2. Okay, the advantage of this new visualization, where I plotted things by their index, is that I can now plot very high dimensional Gaussians. Producing contour plots of, say, a 5-dimensional Gaussian is impossible, at least with current projection equipment, but I can produce a plot just like I showed you, where each one of the columns here, each one of these indices indicates a different dimension of that underlying multivariate Gaussian distribution, and here's the value that each one takes. And here I've just plotted at the top here the contour plot of what the distribution is over the joint distribution over y1 and y5. Okay, so that's this variable here and this variable here. Here's the full covariance matrix. My laser pointer's running out, so I'll hobble over here. Here's the full covariance matrix. And we'll come back to how I've picked the values of that covariance matrix later, but you guys have probably got some inkling of the recipe which I used to generate it. Okay, so now let's have a look at the sort of sampling picture that I showed you before. You can see now we can make exactly the same plot as we draw samples from this now multivariate 5-dimensional Gaussian, and we can do the same thing for conditioning. We can condition on the first dimension of our observations and sample over the rest of them, which now incorporates 4 variables. Okay, so here's where if you hadn't seen Gaussian processes before and you hadn't looked through, seen Neil's talk, you might start to get an aha moment, because we can now consider a 25 or a 20-dimensional, sorry, I didn't do the same number as Neil, I did a 20-dimensional Gaussian here. And I've now plotted the covariance matrix, which I haven't told you how I'm getting, although you're probably guessing, as a color map, where red indicates very, very, very correlated and blue indicates there's no dependency between the variables at all. And at the top here I'm plotting the joint distribution of y1 and y20, and we can sample from it just as we did before. And we can also play our conditioning trick, where we condition on one or maybe a couple of observed variables and sample over the rest of them. And you can see now this function is wiggling around, but it goes through the first 2 points. Okay, so if you had not seen Gaussian processes before, you'd be getting an aha moment at this point, I think, where you said, hang on, this looks a bit like nonlinear regression, because this procedure that we've come up with of sampling from Gaussians conditioned on a bunch of points is giving us back a whole bunch of smooth functions, which goes through the points which we might have observed. We might have observed y1 and y2, and we might want to predict what's going on the other dimensions, and this is giving a recipe for doing that. And here I've just made a very simple picture where I've averaged over those samples, showing the average function here, which has this nice smooth shape, and also I've given back error bars because I could compute variances of these samples as they wiggle around. And this does look a lot like nonlinear regression, where just to reference the equations before, this mean function is actually given to us by this recipe mu star. It's a linear function of our first 2 observed data points, and the uncertainty in this function is given by sigma star using the mathematics I showed you before. So we could either empirically do this by averaging over samples in sort of the pictures that I've shown to you, or we could compute these things exactly using these expressions I gave you to start with. Okay, and we could condition on more points, like the 4 points or 5 points, whatever it was, 4 points I showed you to start with. And you can see, again, we're making nice predictions for a function which is going through these training points, and we're getting sort of the mean estimate of this underlying function with some error bars attached. Okay, so one question is, how the hell did I come up with this covariance matrix? Because this trick, which I've shown you for doing nonlinear regression, really depends on the structure of this matrix. If I'd structured that in a random way, this whole procedure wouldn't have made any sense whatsoever. So this is the form, unveiling of the form of this covariance matrix. X here, I'm replacing the variable index here, which ran from 1 to 20, with potentially continuous variable x, and that's just indexing a continuous version of this index variable, if you like. It's indexing how far along the function we are. And the covariance matrix itself is a sum of two terms. It's our favourite exponentiated quadratic covariance function here, and a sum of some independent Gaussian noise, which I've added on top of it. Okay, and the rationale for writing down a function like that was, well, what we would like is nearby points on this curve to be highly correlated with one another. So nearby points might be, say, the 2 points at the top here, which Neil pointed out, whereas points which are far away, like this point way to the right and this point here, should not be dependent on one another at all, or very, very vaguely dependent on one another. And if we did that, then we'd come up with a way of fitting these data points in such a way that nearby points will tend to be near to each other, and faraway points will tend to be unconstrained by one another, and will sort of smoothly interpolate in between those two things, where that sort of interpolation distance depends on L squared. So importantly, one of the nice properties of moving to this sort of way of specifying covariance matrices is that we can get away from just discrete index sets on the bottom here. So the procedure which I showed you before only handled discretely placed samples. So we're imagining where each one of our observed dimensions was the same distance away from from each other. And we can move to arbitrary points. So this recipe up here for producing the covariance matrix just needs to know how far apart in X space the 2 points are. It doesn't need to operate on this discrete grid. And so what we've ended up defining here is a way of performing nonlinear regression on inputs which can take continuous values. They're not just restricted to a discrete index set. And I've tried to sort of show that here by this covariance matrix now becoming blurry and vaguely continuous, and this line, this function that we're now fitting between these things, is not just evaluated on a discrete set of points. It's actually a continuous function which is going through these points, and we can evaluate it potentially any point. So that, in a way, is the magic of Gaussian processes. We've gone from just simple multi-dimensional Gaussians, rules for conditioning multi-dimensional Gaussians, to a way of fitting a function, doing inference, if you like, in function space. Just to sort of flesh that out a little bit more, and we'll try and go through this more rigorously in a minute, but I want to give you a flavour of what's going on here, especially for the people who haven't seen this before. If we think about this in the normal sort of parametric way of doing regression, what we'd do there is we'd say our y value here is equal to some nonlinear function of our inputs, possibly parameterized by some parameters theta. And if we're general, we might include some noise here. So we might assume that we're not observing the function directly. Maybe our sensors have some noise in them, and we want to take account of the fact that our observations are noisy. And so in this generative process by which we're imagining the data to be generated, we assume it has some corrupting noise, and in particular we'll assume that corrupting noise is of Gaussian form. The purpose of doing parametric modeling is then, in some sense, to estimate this function and then make predictions using that estimate at other points. In those terms, this new method over here is giving us back estimates of the function and uncertainty estimates around it. Okay, so that's this blue line and the shaded area here. Just to be a little bit more detailed, this noise term here, which we put into this parametric model because we wanted to handle noisy sensors, is captured by this noise term here. And this covariance function we drew down here, the exponentiated quadratic, that's really setting down prior assumptions about the subject our nonlinear function to take. And those prior expectations are coded in terms of two hyperparameters, where one of them is this horizontal length scale here, which is sort of the typical length at which we expect this function to wiggle. That's what the length scale controls. We'll go through some pictures of that in a minute. And the second sort of parameter is this vertical length scale here, which is setting, as you remember maybe in Neil's talk, the vertical deviations of that function, how big that function is. Another way of saying it is what's the marginal variance of the function. Great. Okay, so that's sort of the intuitive picture for what's going on with Gaussian processes. Now's a probably selecting those from data. Can we use maximum likelihood or some machine learning method to set those hyperparameters? We'll then build up the rest of the talk from there. So with that in mind, do people have, especially the people that haven't seen Gaussian processes before, do you have questions on this sort of tutorial material so far? No? No questions? Yep.
One question. Can you go one slide back?
Yep.
How do you know this is a nonlinear function with very little noise? It could also be a linear function with more noise.
Great question. We will get to that in a bit, but we'll use probabilistic methods that will enable us to tell us, potentially tell us between those two alternatives. In this particular example, with only 4 points, you might view the fit that we're getting out from this method at the moment using this covariance function as super confident, because there's only 4 points here, and so what you say is quite true. Maybe there's a linear function that just goes through here, and if there were a linear function just going through these points looking like this prediction out here looks rather daft. And we'll potentially give you methods that are able to tell the difference between those alternatives. For these 4 points, with this particular set of assumptions, this is what you get out. For different sets of assumptions, you'll get different things out. So it will depend on what you expect your function to be doing. Any other questions? Yep.
Can I make a non-parametric estimate of the kernel function based on the data, rather than assume it's squared exponential?
You could do. We'll talk about, so there's going to be a talk later on today about how to come up with more fancy covariance functions. I'll tell you about 3 or 4 different covariance functions and ways you can combine them to make more and more complicated covariance functions, and in principle get non-parametric about that. Yep. So there are ways of putting down basis functions in kernel space and having infinite numbers of those basis functions which you use to build a non-parametric estimate of the kernel, so sort of doubly non-parametric in that sense. That's not something we'll get to here, but using the building blocks which I'll show you, you might figure out how to do that. Yep.
Can you just give a general definition of what you mean by a basis function?
Yeah, a basis function, so if you think back to, I hesitate to try and walk over to the, if you go back to Neil's talk, so Neil described sort of a general way of doing nonlinear regression. So if you'd come into this field 5 years ago, maybe 7 years ago, the typical way for doing modeling, nonlinear regression, is to say, let's imagine that our function that we're trying to model is a linear combination of basis functions. And then Neil gave us a particular example of that, where the basis functions were little Gaussians at each point. So a Gaussian here, a Gaussian here, a Gaussian here, a Gaussian here. And now we imagine that each one of those basis functions is multiplied by a linear coefficient, and we try and learn those linear coefficients to best match our function, maybe in some squared error sense. Okay, so it's just a function in X space which we linearly combine in order to build up our nonlinear function which we're trying to estimate. Yeah. I'll go through that again. I'll give some pictures that will sort of complement Neil's treatment later. If it's not clear after that, you should definitely ask questions. Great. That's all questions asked at this point. Okay, so let's just flesh this out with some mathematics, which you've seen before, but this will serve at least to drive it home. So a Gaussian process is just a generalization of a multivariate Gaussian distribution to infinitely many variables. The strict definition here, or more or less strict definition, is a Gaussian process is a collection of random variables, any finite subset of which have consistent Gaussian distributions. So we have this mathematical object which could be over a countably infinite number of variables. If we pick just a finite subset of those random variables, this definition tells us that it will have a multivariate Gaussian distribution, and in particular it will be consistent. So this consistency thing means that the variance vectors we get for that sub have to be consistent with every other subset we could possibly have taken. We can't have 2 variables which are extremely correlated, a third variable which is extremely correlated to one of those 2, and then not be extremely strong correlations by the one we left out, for example. Does that make sense? So you can't have inconsistent sets of Gaussian distributions coming out of the Gaussian process by construction here. Just like a Gaussian distribution is fully specified by a mean vector and a covariance matrix, so I'll be using the same notation as Neil has here. So f is, if you imagine it in terms of nonlinear regression, is our unobserved function, and it could have 1 to n different observations of that function, and we're going to imagine that that's given by a multivariate normal distribution with a mean mu and a covariance sigma. And this is indexed by these indices, as we saw on the previous pictures, 1 through n. A Gaussian process is just a generalization of that, where we're now specifying a distribution over functions, and that distribution over functions has a mean function, which is the average height of a function you'd expect at each point in x space, and a covariance function, k x of x prime, which tells you how correlated or how dependent those two variable at x and a variable at x prime is. And the indices here in this Gaussian process are now not really indices, they're continuous label, just as we saw in the previous example. Now, through Neil's talk, and in fact through all of this talk as well, we're not going to worry about the mean function. So as I said, the mean function just tells you what the average height of a function is at each point. And that's not a particularly interesting property. In some circumstances, it's useful to put it into your model. In general, all of the action is in the covariance matrix, because that's telling you how dependent two variables are at different time points. So we're going to be focusing a lot on this object, the covariance matrix, following up on questions like the one posed from the audience. We're really going to dispense with our mean function and assume it's just 0 everywhere. So the average height of these functions is 0 at every point. Great. Okay. So seeing as you guys seem to know what's going on, let me ask you a question. So we said that a GP is analogous to a Gaussian distribution with an infinitely long mean vector and an infinite by infinite covariance matrix, where I'm not being careful to specify exactly what I mean by infinite here. But that is a useful analogy. How do we go about representing this Gaussian process on the computer? This sounds like a recipe for disaster, right? We've come up with a function which has an infinite extent, an uncountably infinite extent. How can we go about representing that on the computer? So any ideas? How did you guys that implemented it, why was it okay? Why could we still use computers to represent these functions? Any ideas? Yep.
There are two things. Whenever you're using a computer, you're obviously discretizing.
Yep. So,
that, and the covariance function at all scales essentially would capture it's like at all, if you see it piecewise, you can see different sections of it, and it wouldn't matter.
That's true. That might be a useful hack for getting around it. We could just sort of spit our data into different windows and fit nonlinear functions to each of those different windows individually. But I mean, really, we're sort of asking a more theoretical question here, which your first point was getting at, which is a good answer, I think. I mean, even if we have just a small extent, there are an uncountably infinite number of variables between any two intervals on the real line, and so it seems naively, if we didn't have some tricks at our disposal, that this would take an infinite amount of computer power or an infinite amount of memory, because we'd have to be processing all of those variables to some extent. So the answer to this question, and it was touched upon by one of the answers that Neil gave, is that we are really saved by the marginalisation property here. So we know that we're only going to observe a finite amount of data in general, and so the number of training points we have is always going to be finite in extent. And we said we get away with a finite number if we know what region we want to predict in, and we know sort of how coarse we want that prediction to be, how far apart our points are allowed to be, maybe dependent on the length scale in our Gaussian process covariance function. Then we can get away with predicting at a finite number of points as well. And for any practical application, you're probably not going to need to predict everywhere. That seems unlikely. And the marginalisation property of Gaussian says, it's fine, we can just deal with these finite number of points because we can marginalise out the rest of them and forget about them as if they weren't there. So how does that work? Well, let's just flesh this out, how it works for the finite dimensional case here. Imagine we have two sets of variables, y1 which we care about and y2 which potentially we don't care about. Marginalisation is just the property by which we integrate out the variables we don't care about, so they're not represented anymore. And for these discrete variables, for these continuous variables we're talking about here, that corresponds to integrating them away. Distribution over y1, y2, mean of y1 and the mean of y2, and a covariance matrix, which we can also partition into this blocked form. So A is the covariance matrix that describes just the y1s. And what we know is that we can just think about the variables y1 because they're also distributed according to a Gaussian distribution with a mean given. We just go into the mean vector here and read off the top A elements, and that gives us the mean of the y1s. And we just go in here and pick off the relevant part of the covariance matrix, and that tells us what the covariance of those variables too are. And this means that if we extend this to the infinite dimensional case, where maybe we're worried about doing prediction and training on our y1 variables, and these y2 variables are the infinity of other variables that we don't really care about and don't want to represent on our machine because it would take infinite memory and infinite computational power, we can just dispense with them by integrating, and we know that the remaining variables are just distributed in a consistent way according to a Gaussian distribution with this particular mean and this particular covariance. So we only need to focus on these ones we care about. The other ones are sort of hanging around in the background and in some implicit way, but we don't need to do any processing on them or computation on them. So if people say, hey, this sounds like a really bad idea, you go, no, because Gaussians have this consistent marginalisation property, and that's really beneficial for computational purposes. The whole game would be impossible if this were not the case. All right, does that make sense to people? Everyone happy with that? Good. Okay, so here's another question for you guys. All right, so this is a hard question, I think. When we write down the expression for the multivariate Gaussian, the covariance matrix appears in two places. It appears, again, I can't hobble over here. Maybe, I'll do it, it's okay. In two places. Of this way. So the determinant of a matrix is equal to 1 over the determinant of the inverse of the matrix. So I could have written this entirely in terms of the inverse covariance matrix. So the covariance matrix doesn't show up, all that shows up is inverse. So a logical question that someone might come and ask you, in fact it's one of the questions that I first had when I looked at Gaussian processes, why the hell do we bother representing the covariance matrix and talking about covariance functions? Why don't we just talk about the precision matrix, or the precision function if you want to think about that, and just specify a form for the precision matrix? Okay, that would seem like a totally logical choice. It's a fair thing to ask. We could get to pick our representation. We could pick one thing or the other. So what would be the good answer to that question if someone asks you that? Any ideas why we focus our modelling efforts on modelling covariance functions and not on precision matrices or precision functions? Any ideas? Yep.
There's no equivalent. Let's pick this block of the precision matrix when we marginalise everything we don't care about.
Yeah, okay, so that is exactly the right answer. The answer is, for precision matrices, there's no equivalent consistency property. So here we could dispense with the other ones, and we said that the distribution of y1 is, we just go in here and pick out the elements of A and B. For precisions, that doesn't hold. So let me just work you through that and tell you why that's a catastrophic thing, which really prevents us from using precisions in Gaussian processes, at least to specify our prior beliefs. So the precision, as I say, is just the inverse of the covariance matrix. And so for this guy up here, the precision representation for this Gaussian would have a p equal to the inverse of this covariance matrix. So it would be a to the minus 1, dead easy. Now let's look at this guy and figure out what the precision matrix would be for this joint density over y1 and y2. If you go in here and look up this matrix inverse in a recipe book, it'll tell you that it has this form. So it has a very complicated form, which you could go and prove. It's not